Today we're going to be talking about computational difficulty, but in order to do so, we must define what a decision problem is. A decision problem is a problem that can be answered with a simple yes or no answer. Let's talk about complexity classes. A complexity class is a set of problems of related complexity, solvable under the same system constraints. A problem X, so a problem X is in complexity class X, big X, if they share similar characteristics in complexity. A problem is solvable if it runs in polynomial time. So polynomial time refers to things like n squared or things like n cubed. So these are considered doable even though they take a very, very long time. So let's go over our first class here. So notable classes are P. So if that were to be if X is a member of P, so if X is in P, that must mean X's runtime is solvable in something less than something that is polynomial. So something like n squared, where the runtime of X is less than or equal to something that is polynomial. The next class that we're going to be talking about is NP. So NP means that if we're already given a solution, can we verify that solution in polynomial time? So we don't know how to solve it in polynomial time, but can we write an algorithm? So if I give you the solution to a problem, can you write an algorithm that verifies that that solution is correct in polynomial time? So it doesn't mean we can solve it, it just means that we can verify it in polynomial time. NP stands for non-deterministic polynomial time. P, just polynomial time. The next term we're going to be talking about is NP hard. So we're going to be talking about NP hard. What does that mean? It's not necessarily NP, so we can't verify the solution in polynomial time. So it's not guaranteed to be NP. And it's not necessarily a decision problem. So we can't get a yes or no answer out of it. And perhaps it may not even have a solution. So these are difficult questions or things that can't really have an algorithm to describe it or to decisively determine how to solve it. Maybe you ask a coworker, when is your work going to get done? That's kind of a hard problem. The variables in play aren't really situated, it isn't deterministic, so we can't generally write an algorithm towards it. It can be also considered NP hard if we don't think we have the tools on hand to solve it. A problem can be considered hard, but maybe we just haven't understood or found an algorithmic way or some sort of insight into solving that problem. But for now, we might consider it NP hard. To continue, we can say if a problem H is NP hard, so we have a problem H, so an algorithm H, or a problem H that is NP hard, all problems L in NP can be reduced to H. So if H is NP hard, all problems in NP can be reduced to H. In other words, H can run as a subroutine solving all NP. So what does this mean? So if we say that X can be reduced to Y, so if X can be broken up into just Y, that means X can be solved by a subroutine using Y. This doesn't mean that, if we somehow find a polynomial time for, let's say n squared, if Y can run in n squared, so if X can be reduced to Y, and we use Y as a subroutine to solve X, this doesn't mean that overall it's going to be big O of n squared. It just means that we can have a subroutine of Y solve the problem, and the problem might have multiple uses of Y, differences in Y, or we might incur for loops. So just because we have a subroutine of something doesn't mean that the runtime of that subroutine is the runtime of the whole algorithm. So to continue, so remember when X reduces to Y, that means Y can be run as a subroutine to solve X. So Now, it is said that NP hard problems are at least as hard as NP problems. So this means that these are considered usually the hardest problems that we can solve at the moment. So these are the most difficult ones. And because of their difficulty, I will show in a moment some examples of you'll understand why if we can solve these NP hard problems, we can most definitely solve a lot of these NP problems. Now that we've gotten through that Goliath NP hard, I would encourage you to reread it. I'll have a clean version at the end of this video, but I encourage you to really try to understand what NP hard means, which makes knowing this next class a lot easier. So this next class is going to be NP complete, which just means it's NP and NP hard. So we can verify that it's yes. We can verify a yes, and it is NP hard. So it just means, so we can take this definition NP, and we can just cross out the not necessarily NP part. So this makes it NP complete. This is what it means. For our last class, we have solvable in exponential time. So these are things like 2 to the n, where we have n in the exponent spot. These types of algorithms are infeasible for our current day computers. Running this will run out of stars in our observable universe before we finish this program. This just grows way too quickly for our computers to handle. So we call this EXP, so exponential time. And these are some of the most notable complexity classes. For our first example, we're going to be using the halting problem. Now, we're going to have this function below, which may seem a bit contrived, but it's going to help us really understand what undecidability is. So in the halting problem, we're given a function, and this function is going to take a program and its input, and it's going to decide whether that program is going to terminate or not. So we have on line 2 that if this program, so we're going to run the program with its input, if it doesn't halt, we're going to return that this program does not halt. The major red flag is that if it doesn't halt, well, this line 2 is never going to return anything, because when we're running this thing that's running forever, then it's never going to pop out of its frame. So we will never reach this line 3. Lines 4 and 5 show that if it does halt, that it's going to run forever, showing that this line is really never going to happen. That if it does halt, it will just loop forever, and this line and this whole function will never return a thing. So this is to show something called undecidability, that we're not really going to get an answer from this, and if we do, it's going to be wrong and something wrong happened. So this is NP hard, that we don't really get a solution out of this. If you were really trying to write a halting problem or a halting algorithm, still, if something were to loop, there's no way of telling if it looped or not, because we'd never get back a response. We could try to put timers, but this would be band-aids and not decisive. So this relates to something called the dead code problem. The halting problem reduces to the dead code problem, and the dead code problem takes a program and decides, returns what lines of that code are dead or not. The reason why the halting problem reduces to the dead code problem, because if it reduces to the dead code problem, we could use the dead code problem as a subroutine in the halting problem to decide what parts of the code will make the program loop forever. So this too, so the dead code problem is also an NP hard problem. The next problem we're going to be looking at is 3-SAT. So let's ignore the pseudocode at the moment so we can just focus on this example. If you understand the example, the pseudocode will make sense. So what is 3-SAT? 3-SAT is a Boolean satisfiability problem, or SAT, where each clause has exactly 3 literals. So we see 3 literals, and so on. The name of the game is to assign booleans to these literals so that they evaluate to true all the way down the line so that we fully evaluate to true. The problem is that our computer is looking at each literal at a time, so it'll have no idea what the effect of its earlier decisions will be later down the line. Recall the symbols here down, so these are and, or, and not. And this would be a very exciting problem if we could solve, because every algorithm can be reduced to a true or false table. So if we could solve the SAT problem, we could solve every algorithm. Though if we were given a solution, so if we found a solution, we could verify it. We could just run it and see if it returned true or not. So since we can verify it and it's NP hard, this makes this NP complete. And that is 3sat. So here is an example of a function where we're locked in at exponential time. So this is the game of Towers of Hanoi. So this is where we start with n different sized disks stacked in decreasing order over 3 rods. So we have the source, auxiliary, and destination where we want to move it. And the rules are that we can only move one disk at a time. Each turn, a top disk must move from one stack to another. Bigger disks over smaller disks are prohibited. So if we were to start out with this purple one and we were to move it to this middle auxiliary stack, we cannot then go ahead and move this blue to that stack because that would be a smaller disk below a bigger disk. So the name of the game is to try to get this source, this whole entire stack, moved directly to the destination while following the rules. The last problem we're going to be talking about is the traveling salesman problem, or TSP. So this is given a list of cities and distances between each pair of cities. What is the shortest route that visits each city exactly once? So we visit each city exactly once and returns to the origin city. This problem is NP complete. So say we have this graph and we wanted to find the shortest path between all cities. So these weights could be the distances. So we want to find the shortest path between all cities and visit each city exactly once. Well, we have other things in algorithms called the MST, so the minimum spanning tree. The minimum spanning tree connects all nodes by edges that are the most cost effective, but this isn't the solution because a lot of the times it's going to revisit these same edges as we'd have to go down and come right back up. The solution is right here on the right as we visit each city exactly once, return to the origin city, and it is the most cost-effective route. This is verifiable, so this is NP, so if we are given a solution, we could just run the solution, but how do we verify the solution? Well, we can write an algorithm that says, okay, does this solution, so is this solution, does the solution have a cost that is at least less than or equal to 9? Or less than or equal to k. Less than or equal to k. That's how we solve NP verification problems. So does this path visit all nodes once, returning to the origin in less than k units? So that's how we write NP verification problems, or specifically for this one. There are other ways to verify problems, but this is a common route to do so. So this is TSP, or the traveling salesman problem. So we want to go ahead and relate these complexity classes to each other. So P, NP, and EXP, so exponential time. So if we were to write these in sets, we can say for problems, there are problems that are, solvable in polynomial time. But on the flip side, there are a lot of problems which for the moment we know that are verifiable in polynomial time, but we don't know if we can solve them in polynomial time. We can verify them, but we cannot solve them. And then we have exponential time algorithms where we don't know if we can verify all exponential time algorithms in a polynomial time. So we don't know if all exponential is NP, but it may encompass some of those problems. And this is the general consensus at the moment of what these spaces look like. It could be possible, it could be very well possible that, NP and P share the same space, that, all NP is P, but at the moment, we just don't know. We don't know if this is actually true or not. So this first one is saying this, that if you are P, so if you are here, this means that you are NP, that, if you're solvable in polynomial time, that means you are also verifiable in polynomial time. But if you are NP, this does not mean you are P. We can verify you in polynomial time, but this does not mean that you can be solved in polynomial time. This diagram, however, says that. This one says that, if you are P, then you are NP, and if you are NP, then you are also P. But at the moment, we just don't know if this is true or not. We just don't know, so we don't say this. And the other possibility could be that exponential time shares the same place with NP, and P is all by itself. But again, this is another one of those we just don't know, so we don't say. But here on the left, this first one over here is the general consensus on the space at the moment. And that is the end of this video. If you enjoyed it, don't forget to like and subscribe. For a concise rendering of this textbook and a cheat sheet, in the description below is an open source textbook for anyone to contribute to. These videos are more up to date, so if you find any discrepancies, feel free to open a pull request or issue a GitHub issue. And with that, thank you.